Indiana University East School of Natural Sciences and Mathematics. Average atomic mass. So let's think about an example of carbon. Okay, either diamond or graphite, I don't care. Within each, if I take a chunk, am I going to get pure carbon-12? No. I'm in fact going to get a mixture of carbon-12 and carbon-13. So out of every 100 grams, I'm going to get 98.9 grams of carbon-12 and 1.1 gram of carbon-13 and a little bit of carbon-14. So what we have here, okay, is that we have the percentage of atoms of each isotope, and that is called its abundance. Okay, now in practical terms, what we want to do is to find the average mass of any atom we pick out. So what we want is essentially a weighted average mass of atoms. Okay, and that is what we refer to as a relative atomic mass. How do we find out this information though? What we do is we actually use we get a mass spectrum here. In a mass spectrometer, what this does is it basically separates out different isotopes into different beams, and you get a detecting screen. And what you get is what's known as a mass spectrum, shown here, that shows by the intensity of the peak tells you what the abundance of the isotope is, and you get the atomic mass along the x-axis. So the atomic mass unit is defined in such a way such that the mass of a carbon-12 atom is 12 exactly. And then we define the mass of an atom as the mass of an accordingly based on this relative scale. Note that for reasons we might go into when we look at chapter 20, nuclear chemistry, you see that the mass of different atoms is not going to be integer values, but that's not very important at the moment. But what we need to realize is that the average atomic mass of a given element is the weighted average. So what that means is that this value, which is what we see published on the periodic table, is given by averaging out. So what you do is you assume you have 100 atoms. So in this case, so the average atomic mass here, okay, is this. So out of 100, so that's my denominator because I'm averaging over that. Out of 100 atoms, I have 7.59 atoms of lithium-6, 6.0151 AMU, plus 92.41 atoms of 7.0160 AMU, and that comes out to be 6.9400 AMU. So, and that is the value that is reported on the periodic table. So to recap, each time you assume you have 100 atoms, then your relative abundance as a percentage shows up here, and you multiply each by the atomic mass of that isotope, and you add it up together and divide through and get that.